Sasha, hello. Саша, привет. О, два Саши даже. Саша, привет. Оба Саши, привет. Hello.
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 Алло.
Алло, привет, Саш. Тут два Саши, Полищук и Нанонен. То есть, это сейчас я к Саше Полищуку обращаюсь. Ага. Саш, все нормально? Хочешь попробовать два экрана как? Сейчас. Алло. Oops. Okay, so it's my big pleasure to introduce Sasha Polishchuk from University of Eugene in Oregon. And Sasha will speak about hyperelliptic limits of quadrics through canonical curves and super short locus. Thank you, Sasha.
Okay, thank you very much for the invitation. This will be a talk based on two different joint works. So one will be a work joined with Eric Reins and another work joined with Giovanni Felder and David Kazhdan. So it starts with so my talk will also kind of roughly consist of two parts. So the first part will be about very classical subjects, quadrics through canonical curves. And the second part will be about application of this to super curves. So the second part is joined with Felder and Kazhdan. Okay, so let me start. So part one is about canonical quadrics. So suppose we consider a non-hyperelliptic curve of genus at least 3. So then it has a canonical embedding. So C embeds into PG minus 1 by the canonical linear series. And we can consider quadrics through this curve. So we can consider quadric hypersurfaces passing through C, quadrics through C. And so we can actually calculate exactly how many because we just consider the multiplication map. So from global sections of canonical line bundle, well, actually from maybe symmetric square of these two global sections of the twice canonical line bundle. And so I will always call this map mu. So so when you have non-hyperelliptic curve, this is surjective, and so we can calculate exactly how many the dimension of the kernel. So, and this will be this quadrics through C. Yeah, so so dimension we can calculate. So dimension equals G times G plus 1 over 2 minus 3G minus 3. So, right. So, for example, if genus equals 3, there are no quadrics. For genus equals 4, there is 1. For genus 5, there is 3, and so on. So now, however, when you consider hyperelliptic curve, so now suppose C, let's call it C naught. Suppose it's a hyperelliptic curve. So then this multiplication map mu is no longer surjective. So no longer surjective. And so the number of so dimension of the kernel jumps. So we can actually calculate exactly by how much. So because so if C naught has a double covering over P1 map, so we have a map F from C naught to P1. So then canonical class of C naught is the pullback of G minus 1, and all global sections come from pullbacks from P1. However, when you consider twice canonical line bundle, They will not be all pullbacks, so you can actually calculate that the dimension of co-kernel of mu is equal to g minus 2. So the dimension of kernel jumps by g minus 2. Okay, so dimension of kernel becomes larger, is larger than for non-hyperelliptic C. And this raises a very natural question. So what if I consider now, so my hyperelliptic curve can be obtained in many ways as limit from non-hyperelliptic one. So I can consider families of curves which are generically non-hyperelliptic and that have hyperelliptic center fiber. So I can ask and of course I can arrange that the quadratic, some families of quadratic relations along this between global sections of K, such that they vary along in the family, and so I get some limits of non-hyperelliptic quadratic relations. And the question is which of this which of this bigger space of quadratic relations on hyperelliptic curve can be deformed into non-hyperelliptic direction. Okay, so this is the main question. So which hyperelliptic quadratic relations in symmetric square of in kernel of mu are limits of non-hyperelliptic ones. Okay, so this is a very classically formulated question, and surprisingly, we didn't find an answer in kind of classical works on this. So, and it has actually very pretty and nice answer. Okay, so let me explain the answer. Okay, so to explain the answer, I have first. So there is a certain way to understand. First, I need to understand certain identification of this space of quadratic relations. So kernel of mu for hyperelliptic curve. So, all right, so how do we do this? So basically, in this case, this is nothing else but kernel of multiplication map on P1. So on P1, I take sections of O of G minus 1, right? And so I take symmetric square going to H naught on P1 of O of 2G minus 2. And so there is a very simple way to generate all such quadratic relations, namely, right, so suppose I have homogeneous coordinates x0, x1. So this is really not coordinate dependent, but it's easier to state using coordinates. So homogeneous coordinates on P1. So then there is a natural quadratic map from H naught of O of G minus 3, so polynomials of degree at most G minus 3 on P1, to this kernel. So this is not a linear map, this is a quadratic map. So what do we do? So we take this polynomial and we send it to x square x naught square times p. Okay, so I'll denote by star multiplication in the symmetric algebra of h naught of O of g minus 1. So here we take x1 square times p, and then subtract x naught x1 p times x naught x1 p. Okay, so it's clear that if you multiply this out to sections of O of 2g minus 2, both times you'll get x naught square x1 square p square. So this is really in the kernel of mu. And this depends quadratically on p. So this means that this defines the linear map from the symmetric square of h naught p1 of g minus 3 to the kernel of mu, and this map is easily seen to be an isomorphism. Okay, so now, it means that we can consider these quadratic relations themselves as quadratic forms, on homogeneous quadratic forms on the space of dimension g minus 2. And so the answer now finally is the following. So the answer is that Q in kernel of mu is a limit of non-hyperelliptic quadratic relations if and only if Q viewed as a quadratic form on G minus 2 dimensional space is degenerate. Is degenerate as quadratic form on H naught P1 of G minus 3 dual. Okay, so degenerate means that yeah, if you write it as sum of squares, it will be less than g minus 2 squares. So it will be at most g minus 3 squares. Okay, so this is the theorem. Okay, I should have formulated as a theorem. So this is a theorem in our paper with Eric Rains. Okay, so any questions so far? So I'm now going to explain the proof. I hope the formulation is clear. I don't see anyone raising their hands. Actually, I don't see anyone.
All fine, Sasha. I think no problem.
Okay. Okay, great.
Well, can you give me some time to understand what is degenerate as a quadratic form? Or...
Degenerate as a quadratic form. So you have a quadratic form on n-dimensional space. So degenerate means that if you consider the corresponding symmetric pairing, this pairing has a kernel. Or if you like, choose a basis, write a matrix, and this matrix should be degenerate.
Okay.
Determine 0.
The corresponding
it was obvious, but just to take time. Okay, thank you.
Mm-hmm.
Yeah.
Sorry, what was the question?
Yeah. Okay, I understood. So it's an element of S2 of, but I don't understand because it's a quadratic form on OG minus 3, and I thought that this is in S2 of G minus 1.
So so what we define is a linear embedding. So this sits inside a square of H naught of OG minus 1 as well, but we do not view it as a quadratic form on H naught of O of G minus 1, but as a quadratic form on O of G minus 3, because we're only looking at this kernel of mu, and kernel of mu has its own presentation as quadratic forms.
Okay, thank you.
Okay, so in principle, so we actually have, so there are two parts to prove, right? So two directions. So first, if we have Q naught, which is deformable, is a limit, is a non-hyperelliptic limit. Then Q naught is degenerate. And this, in principle, can be proved by sort of more or less standard tools of deformation theory, but there is a very neat geometric argument which I want to present. By the way, I want to maybe comment also one thing about this theorem. So it's slightly stronger in the following sense. So in the case when we say that Q is a limit, we actually, so when it's degenerate, right? So then we claim that there is actually an algebraic family such that it realizes it as a limit. Whereas in the case when the quadric is non-degenerate, not only it cannot be deformed to algebraic family, but in fact it cannot be even deformed to order one. So there is not even any infinitesimal deformation in non-hyperelliptic direction. Okay, so let me first explain why if Q naught is a non-hyperelliptic limit, then it should be degenerate. So this uses so the proof uses so-called ribbons, or more precisely, rational ribbons. So these are curves which are non-reduced. So these are certain non-reduced curves. Which look like double thickenings of P1. Okay, so they were introduced in the work of Bayer and Eisenbart in '95. And I think the primary motivation was that they could be useful in studying syzygies of canonical curves, because ribbons also have canonical embeddings, and they kind of behave as generic curves in their canonical embedding. Well, at least like for each Clifford index, there is a ribbon that behaves like a canonical curve with this Clifford index. So they hope to prove results about generic curves using ribbons, and indeed this worked eventually. So I think just maybe a couple years ago there was a work of Anand Depurkar who did prove the conjecture about syzygies of ribbons. Anyway, so we are not going to look at syzygies. So first, let me explain what they are. So so a ribbon. So as a topological space, this is just P1. Okay, so there's going to be a non-reduced curve such that when you consider it a reduced scheme, you just get P1. But when you look at the structure sheaf of the ribbon, so it maps to O of P1, and there's going to be a kernel which is a square zero ideal, and this ideal itself can be viewed as a sheaf on P1, and it's going to be a line bundle on P1. And in fact, so if I'm looking at ribbons of genus G, so the kernel is going to be a line bundle O of minus G minus 1 on P1. Okay, so this is how the structure sheaf of a ribbon may look. So for example, there is a simplest ribbon where you just have take a direct sum of P1 plus O of P1 minus G minus 1. So this ribbon has a property that there is actually a degree 2 morphism from R0 to P1, and for this reason, obviously, it's called hyperelliptic ribbon. But there is just exactly one hyperelliptic ribbon, the split one. So Bayer and Eisenbart prove that every non-hyperelliptic ribbon, so every other ribbon, kind of every non-split ribbon, actually admits a canonical embedding into projective space.
Why it's not only one? Because the ring structure is there. So there should be a polynomial of degree 2g plus 2 to give the ring structure.
No. But I require.
It's nilpotent.
I require that this is a square zero ideal.
Okay, square zero. Okay, thank you.
So this is in general definition of a ribbon. I require that this is a square zero extension of OP1.
Okay, thank you.
Yeah. Okay, so any non-split ribbon actually has a canonical embedding. So it's Gorenstein, and so the canonical class gives an embedding into PG minus 1. And so it's going to be a thickening of, so its image is going to be a thickening of rational normal curve in there. So I will write that it contains CR. So CR is going to be a rational normal curve. So just, so it's really P1 embedded by its Veronese embedding. And so to understand the so actually to for our theorem, I need to explain understand better the canonical image of a ribbon. So this double thickening of rational normal curve. So and to understand this, there is an important calculation which is in by Reisenbad already. So and the calculation is of the normal bundle or conormal bundle to the rational normal curve. So this is important calculation. So if I consider rational normal curve inside PG minus 1, so its conormal bundle, so J CR over J CR squared, it has a canonical identification of the following kind. So I identify it with P1, of course. So it's going to be just a direct sum of copies of line bundle of minus G minus 1 on P1. And the number of copies, it's going to be G minus 2. And so more canonically, you can write it as sections of O of G minus 3. Okay, so this is a vector space. And then we use it as a multiplicity for the line bundle of minus G minus 1. Okay, so now a ribbon corresponds to a functional, or lambda, corresponds to a functional lambda, a non-split ribbon corresponds to functional on O of G minus, on sections of O of G minus 3 on P1. Okay, so in fact, hyperelliptic ribbon also, so this can be done independently from canonical embedding. So lambda equals 0 would correspond to hyperelliptic ribbon. But for non-hyperelliptic ribbons, so we can just consider this non-zero functionals. And then the structure sheaf of a ribbon is very easy to understand. So we start with a double thickening of, of the rational normal curve. So we take O of PG minus 1 modulo G square. So this is a double thickening of the rational normal curve. And then we use our functional lambda. So using this identification of conormal bundle for every functional lambda defines a morphism from here to O P1 minus G minus 1. And so I take the push out, and this gives me the structure sheaf of a ribbon. Okay, so this description is very convenient, and it is related it is related to our identification of quadrics through rational normal curve in the following way. So recall now that we have identification of, so this kernel of mu that we were considering for hyperelliptic curve. This is nothing else but quadrics through the rational normal curve. So H naught of JCR of 2. And so we can ask when such a quadric passes through a ribbon lambda. So given lambda, so suppose I have an element here, Q. So given lambda in H1 P1 of G minus 3 star. So it's very easy to see from the above description that Q passes through the ribbon R lambda if and only if when I differentiate Q in lambda direction, I get 0. So here I identify, I can also view this Q as I explained before as an element of S square of H naught P1 of G minus 3. So it's a quadric precisely on this quadratic form, precisely on the space of G minus 3. So I can differentiate it in direction lambda. And so when I get 0, this precisely tells me that this quadric passes through R lambda. So in other words, I can now, yeah?
Lambda is in H0, not in H.
Oh, yeah, thank you very much. Yeah, this is a typo. Thank you. Yeah, of course, H naught. Yeah, no H1 should appear yet. Okay, so so now, in other words, I can now, so I can get closer now to my main point. So we observe now that a quadric is degenerate. So Q is degenerate as a quadric on H naught of G minus 3, if and only if it, when I think about it as a quadric through rational normal curve, then it passes through some ribbon. Q passes through some R lambda with lambda not 0, so some canonical ribbon. But this is already very, very close to what we want for the following reasons. So now the main point, kind of main geometric point, is the following: that if suppose I consider degenerating family, so suppose I have kind of C over some DVR, so some family degenerating of non-hyperelliptic curves, kind of generically non-hyperelliptic, of generically non-hyperelliptic curves with hyperelliptic limit, with hyperelliptic C0. So then you can consider the family of the corresponding canonical curves. So you get the family of canonical curves. So I can either kind of consider, I can either trivialize the Hodge bundle over this family, or I can do this relatively in a relative Hilbert scheme. So I can view each, so I can consider the point of the Hilbert scheme corresponding to each canonical curve. So each canonical curve defines, so let's see, over S. So each CS defines a point in the Hilbert scheme. And so therefore, there is actually a unique limit. So there exists a limit in the Hilbert scheme of subschemes of PG-1 that have the same invariance as the canonical curves. So there exists a limiting curve in the Hilbert scheme. And the claim is that this limiting point is a ribbon. So claim lim C is a ribbon for some. Okay, so if you believe this claim, then you immediately derive the proof of what I wanted. So what did I want to prove? I wanted to prove that if I have a quadratic relation between differentials and hyperelliptic curves that can be deformed, then the corresponding form is degenerate. Indeed, so it comes, so this quadric kind of passes through all these canonical curves, therefore it passes through the limit, but the limit is a ribbon. So therefore it passes through some ribbon, and as we just discussed, this means that the form is degenerate. Okay, so is this, can you follow this? Is this okay? Yeah, so this was the main idea of the argument. So again, so once you know that your quadric is a limit of, yes?
Does it give you a complete description of the closure inside the Hilbert scheme of the space of canonical curves?
No, I think there could be more complicated limits.
You mean that the limits could be reducible?
Yes,
right?
they can become, yeah, the curve can become stable curve, and then the stable curve can somehow, yeah, so no, there are more complicated limits, obviously, yeah.
But is it possible to describe it completely?
Yeah, we did not try that, but it's a good, I think it's an interesting problem. Yeah, but at the very least, you will also get just stable curves in there, right? But this is still not it. So you will have to somehow glue various ribbons. So you may have kind of, yeah, I'm not sure this is, I'm not sure how to do this, but it's an interesting question. All right, so yeah, so let me now explain this claim very quickly. So proof of claim is the following. So we have this, so we consider this family of curves, and it has a project, so each of them has a projective embedding. So so we consider, sorry, not projective embedding, each of them has a canonical map. So we consider this canonical map. So yeah, so this is going into kind of projective space over S. And the point is that this map is going to be injective everywhere except at the central fiber. So if I consider F naught, this is going to give me a hyperelliptic curve. So it's going to factor through rational normal curve sitting inside PG-1. But nevertheless, I can still consider still consider this map from structure sheaf of PG-1 over S over this base of the family to the push forward of structure sheaf of C. And this map is not quite surjective. It's surjective away from the special fiber. So, and then we just consider, so we define, so consider the image of this map. So this will be, so it will be a structure sheaf of some subscheme in this relative projective space. So how do I call it? So C prime. So there will be some, away from the special fiber, it will be still the same C. And then you can easily calculate that this, so this C prime is still a flat family. And then from this picture, when you calculate the special fiber of C prime, you will see that this has a map of P1 to this rational normal curve. And then you can see that in fact C prime is supported on the rational normal curve. Sorry, on P1 sitting, which is the rational normal curve sitting inside PG minus 1. And then kind of, it's very easy to deduce that in fact it's going to be a ribbon. So looking at the Hilbert series, looking at the description of the conormal bundles, so you can see, sorry, this is C prime 0, the special fiber. So you see that this will be a ribbon. Okay, so I'll skip the proof of the second part of the proof that that if the curve is, if the quadratic relation is non-degenerate, then in fact you cannot deform it. So this uses some global considerations plus calculation of tangent spaces. So let me now, I think it's time for me to pass to the second part of my talk. So about supercurves. Okay, so surprisingly, this result has some applications corresponding to super period map for supercurves. Okay, so what are supercurves? So this was a very popular subject in Moscow in the 80s and has been less popular lately. So I should probably remind what are supercurves. So they're also known as supersymmetric curves or super Riemann surfaces. So these are the following gadgets. So everything. So basically, you should place yourself in the supersymmetric world. So everything is Z2 graded. So you consider kind of analogs of sheaves, analogs of schemes based on Z2 graded supercommutative rings and so on. So when we define what is a supersymmetric curve, so first of all, this is a smooth scheme of dimension. So okay, so it's always in families. So so it's a super scheme over some super base S, so of relative dimension 1, 1. So it means that kind of locally in classical topology. So yeah, if I work over C, I guess I'm going to work over C. So locally in classical topology, X is given by, so kind of has relative coordinates, one even coordinate, one odd coordinate. So yeah, so it's smooth, so which means that when I consider the Kähler differentials, it's locally free of rank 1, 1. But the main point is that there is an extra structure here. So an extra structure is a distribution. So it's a subbundle inside the relative tangent bundle. And so tangent bundle has rank 1, 1, and the subbundle should have rank 0, 1. And so on the tangent bundle, you have a supercommutator. And so the condition is that this distribution is maximally non-integrable. So it means that when you consider supercommutator map, so you can restrict it to D tensor D. And then you map it to T modulo D. And this should be an isomorphism. Okay, this is the condition. So locally, we can choose relative coordinates. Coordinates Z theta, where z is even, theta is odd, such that d is generated by the vector field partial derivative with respect to theta plus theta partial derivative with respect to z. So there is always this normal form locally. And another way to view this data is the following. So if you consider dual to the embedding of d into t, you will get a morphism from omega 1 xs to d dual, and d dual can be canonically identified with relative dualizing sheaf, which is itself obtained as by some kind of super determinantal construction from the relative cotangent bundle. Okay, so this is relative dualizing sheaf, and so you can think of this as a derivation, because it's a homomorphism from omega 1. So you can think of this as a derivation with values in the relative dualizing sheaf. So this is a derivation. Okay, so let me quickly, before I lose all the people who like classical geometry, so let me quickly explain the relation of this to spin structures. So if the base is even, so when S is even, so there are no odd coordinates, then this super curve over S is the same as a usual smooth curve over S together with a spin structure. So this is as follows. So the structure sheaf of X is going to be a structure sheaf of C plus a line bundle. So, but this time this is not square zero. Yeah, this is, sorry, this is still square zero extension. So so this should be viewed as odd part, OC is even part. And this L is the line bundle on C, which is equipped with the isomorphism of its square with a canonical bundle on C. So it's a spin structure. And so the structure derivation is given as follows. So the dualizing sheaf of X over S is given as omega C plus L. And it's actually a line bundle. So it's generated by, so L is again odd part, omega C is even part, and so the OX structure is given by multiplication L tensor L to omega C, which is precisely the spin structure data. And so the structure derivation goes from OX to omega X. So you start here with a pair of function and S, where F is OC and S is an L. And you map it to df, just usual de Rham differential, and here you just S remains S. Okay, so this is how this looks over bases with no odd coordinates. But the whole point is that these super curves vary in families where you have some odd coordinates on the base and there are non-trivial variations. So in fact,
Sasha, there are some questions in the chat. Do you want to
yes,
answer them now? Or, yeah?
Yes, let's answer them now.
Should I read or can you read? Let me know.
I don't see.
Okay, so one question is, what is the rank of the dualizing sheaf of the smooth?
Very good question. Its rank is 0, 1. So it has one odd generator. So it means that locally it is locally free sheaf with one odd generator. Any other questions?
There was a second question just now. Would you mind saying the rank in general for Mn?
So for Mn, I think the dualizing sheaf is going to be either 1, 0 or 0, 1, depending on parity of n. So when n is odd, it will be 0, 1. So the question is in the number of odd directions of odd variables in the. Okay, great. So
Thanks.
let's move on. Right. So when you look at the moduli of supercurves, so we can consider moduli. So we can vary them in smooth families. And so when you look at the infinitesimal deformations, so the tangent space. So over a point, any curve is just going to be this usual curve with a spin structure. So so the tangent space at CL. So you're going to have even directions are going to be the same as before. So this can be even part, H1 of C omega C inverse. So this is even part. But there will be also odd directions. So odd directions, you have to take H1 of L inverse. So this first space has dimension 3g minus 3, and the odd part has dimension 2g minus 2. So the moduli of supercurves has super dimension 3g minus 3 and 2g minus 2. Okay, so now I want to discuss the super period map. So for this, I need to consider the kind of analog of the RAM resolution. So if I have this x over s, so I can consider kind of constant shift along fibers. So going into, so this is really, so if this is map is pi, so this is really pi inverse of OS. So this embeds into structure shift of x, and then I use this derivation delta above, and I use it as an analog of the RAM differential, and this is going to be surjective. So this is a resolution of the constant shift in fibers. So then if I look at the long exact sequence of high direct images associated with this, I get, so part of this will be so it will be pi star of omega xs. So this is a kind of analog of Hodge bundle going into R1 p star of CS. So this is just a vector bundle associated with the local system on the base, corresponding to the corresponding family of H1s of the underlying curves. And here I have R1 p star of OX. Okay, so now, so in the for the usual family of smooth projective curves, this will be an exact sequence. So here there are some problems because in principle, global sections of the structure sheaf is not necessarily just constants. So when you look at the just single curve, so for curve over C, super curve over C, so when you look at the OX, so then this has even part, which is H0 COC, and then it has odd part, which is H0 of the corresponding spin structure. And the spin structure sometimes have sections. So this is possibly non-zero. So I'm going to throw away this locus of super curves corresponding to spin structures with non-zero sections. So when I throw this away, everything works as in classical case. So I will just get this exact sequence. Okay, so consider open locus U in this model of super curves. So this corresponds to CL with vanishing global sections. So then we actually have exact sequence. So over U, we have exact sequence of this pi star omega x going into R1 p star Cx going into R1 p star OX. So we actually get a subbundle. So this is the usual kind of, this corresponds to, this is a vector bundle associated with local system of rank 2G. So purely even rank, so there is no odd rank. And so this is going to be a subbundle of rank G0. And what we can do is we can go to covering where this local system is trivialized, and then we can view this just as a varying subspace in a given vector space. So this maps to Grassmannian, or more precisely, it goes to Lagrange. So this subspace is going to be isotropic, so it goes to Lagrangian Grassmannian in 2G dimensional symplectic space. So after we pass to this covering. And so this is kind of the analog of the, so this is the analog of the classical period map. So I will call this a super period map. Right, so then, so yeah, so this is kind of analogous to looking at the, so if you choose basis of homology, right? So you just so this corresponds to looking at the corresponding period matrix of global of integrals of global differentials along A cycles, something like this. But except that now this is a map from some. So on the left here I have a super space. So this is as 3G minus 3 odd even dimensions and 2G minus 2 odd dimensions. On the right, I have something completely even dimension. But nevertheless, this is a morphism of supermanifolds. So locally, this means so that so I have some functions on this Lagrangian Grassmannian. I pull them back, and I get some even functions on this super space. So I can therefore consider the scheme image. So we can consider scheme image. So yeah, if we restrict this map to the reduced space, so here I can consider reduced subscheme. So then this reduced subscheme maps to the usual modular space of curves, and so the corresponding map is just the usual period map. So therefore the scheme image of the super period map, it contains the scheme image of the usual period map, which is called the Schottky locus of the classical period map. So here I just consider right. So I basically I have this ideal of functions on Lagrangian Grassmannian, which I will call ideal of super Schottky locus. So this is ideal of functions such that their pullback is 0 under the super period map, and it is contained in the ideal of the usual Schottky locus. So these are functions such that their pullback under the classical period map is 0. And so it's actually an important extension. So it's easy to see that if you, because there is 2G minus 2 odd directions, so if I raise so if I have any function on Twiddle which becomes 0 on the reduced part, if I raise it to the gth power, it becomes 0. So therefore, in fact, here I have the containment that the jth power of the usual Schottky locus, of the ideal of the usual Schottky locus, is contained in the ideal of the super Schottky locus. So the question is whether this G is actually the minimal power like this, and the theorem, which is the theorem from our paper with Felder Kazhdan, is the following. So we can actually estimate the minimal power needed so that ideal of Schottky locus to this power is contained in the super Schottky locus. So minimal m such that ideal of the Schottky locus to the m is contained in the ideal of the super Schottky locus is okay, so it is actually G if G is odd, and if G is even, we can only say that it's either G or G minus 1 if G is even. So here we have a slightly weaker result. Okay, so the proof is based on the study of the second variation map of the super period map. So why second variation? So kind of second variation in odd directions. So the point is that if you just look at the derivative of the period map, of the super period map, so the part of the derivative going from the odd part of the tangent space is automatically 0 because the target has no odd variables. So whenever you have a kind of map which has derivative 0, it makes sense to look at the next stage, at the quadratic part. So this is what we call second variation. So it turns out that this second variation, so we can think of it like this. So right, so we have to know something about the tangent map to the usual period map. Okay, so the tangent map to the classical period map. So rather I will write it as a dual map. So it goes from, so I'll write it as a map from the cotangent to Lagrangian Grassmannian to the cotangent space of the MG. So this is actually a very well-known map. So cotangent to the Lagrangian Grassmannian can be identified with S square H naught K on the curve. And the cotangent to the MG, this is quadratic differentials, H naught of C K squared. And this is just multiplication map. So now the second variation map goes from the kernel of this, from the kernel of the tangent map to lambda square to the quadratic expression in odd directions that we have, and these odd directions, they are odd directions are H1 of L inverse dual. So, or using Serre duality, I can think of this as, yeah, so, yeah, maybe I'll just write it like this, yeah. So now the whole point is that we want to get information about the second variation. So this, what is the meaning of this quadratic form? So an element here, so this is a linear part of some equation of the usual Schottky locus. So this is a linear. So if I have an element here, I can think of this as some function on kind of local function on the Lagrangian Grassmannian passing through classical Schottky locus. Image of period map, classical period map. So then when I pull it back to the, so I pull back X to the superspace, to kind of modulo of supercurves. So locally, it will start with some quadratic expression in odd variables. So there will be some quadratic form in odd variables, of which we have 2g minus 2, and then high order terms. And so this quadratic form is precisely given by the second variation map. Okay, so this goes to some q of theta 1, theta 2g minus 2. So basically, if I prove, for example, that for some curves and spin structures, I can make this quadratic form non-degenerate, then this would imply that I need at least gth power to kill this. So if I need to raise, so if q is non-degenerate, then minimal m such that x to the m becomes 0 is g. Okay, so therefore it is important to calculate the second variation map, and this in fact can be done. Well, so we can write some formula for any curve, but in order to calculate explicitly the rank and so forth, you need some very concrete information on this kernel of mu. So you need some concrete presentation of the quadratic relation between elements of H naught k. But this was precisely what I was discussing in my first part, namely, so if I take curve to be hyperelliptic, so the problem is yeah, so if I take a curve to be hyperelliptic, then I can actually describe very precisely kind of quadratic relations and when they're deformable to non-hyperelliptic ones. So that's precisely what I do. So we calculate this second variation map on hyperelliptic curves using explicit description of quadratic relations. And then we take the ones which are deformable, and this way we prove something about what happens for generic curve. So that's basically the idea. So from this we derive that for generic curve we'll have okay, for odd g at least we can prove that this quadratic form will be non-degenerate, and therefore you need at least g's power to kill it. Okay, so maybe I'll stop here.
Sasha, thank you. Let me thank Sasha in Zoom like this. Thank you very much. And before I ask for questions, let's check some question in the chat. Do you want to read it or do you want me to read it?
Yeah, I see them now. Yeah.
Yeah.
So what happens if you drop H not L equals 0 assumption? So the first thing that happens here is that this sheaf P star omega XS, it stops being a vector bundle. It will be some coherent sheaf, but it will not be locally free. So you cannot. So this construction does not go. So in fact, our paper with Felder and Kazhdan has another part where we study precisely this question. We study what happens, what kind of poles does the superperiod map when you approach this divisor where the spin structure acquires sections. So it turns out that you can describe the polar behavior of the superperiod map, and this has applications to the super measure on in superstring theory. But this is a completely different story. But anyway, so maybe just to answer your question, basically yes, so there is a question also about odd spin component. Yeah, so for odd spin component, there is no superperiod map. So it's just completely not defined there. Okay, so the second question, for quadrics through the hyperelliptic limit, can you see them from the corresponding family of Jacobians. So I'm not sure I understand the question. What do you mean by seeing quadrics from the family of Jacobians? Ah, double points of theta divisors. Yeah, I don't know. Yeah, sorry, I don't know the answer to this question. Yeah, this is a good question.
Okay, any other question for Sasha? Yeah,
Maybe I
Fabrizio?
have a question or
Yes.
What happens if you go to a stable curve, which is a G-1 curve plus an elliptic tail? Did you do the calculation in that case?
You mean for which part? For quadrics or for
this M, for this M?
For super period map?
Yes.
Ah, no, we did not do the calculation there, no. Yeah, I see. So yeah, but so yeah, the first question is whether the super period map is even defined there. So probably yeah, so when you go to stable curves, you have to be more careful. First of all, you have to check indeed that the super period map is defined.
Okay, thank you.
Yura, do you have a question, or you just turn on the microphone?
Okay, I see another question. I see another question in chat.
Okay, let's go to chat. Yeah.
An integrable system characterization of the super Schottky locus. And is that sufficiently explicit? Okay, so look, we're just in the very beginning of understanding anything about the super Schottky locus. So first of all, yeah, and is that sufficiently explicit to try to address? Yeah, this is all very good questions, but you see, I think we're just in the very beginning of trying to understand anything about the super Schottky locus. So one other thing we understand is that the ideal of the super Schottky locus is actually contained in the square of the ideal of Schottky locus. This is proved by Codogni Viviani in their paper. And so, yeah, I don't know, for example, how many local equations you need for the super Schottky locus. We know very, very little about this. So I guess the first case maybe one should study is of genus 4. So in genus 4, so it sits somewhere between the fourth power of the so Schottky locus in this case is just generated by one equation. So and it sits somewhere between the fourth power and the second power. Most likely it sits between fourth and third power, which means that it would correspond to some subscheme of just the Schottky locus, and I don't know what it is. So yeah, it is still, I think, too early to ask questions about relations with integral system. But of course you can. Yeah, I don't know. I think it's an interesting direction to think about.
Thank you. And any more questions to Sasha? Okay, if not, let's thank Sasha again. Thank you very much. Thank you for a beautiful talk, and thanks. And let me just remind you that on Thursday we have talk by David Mumford with a question and answer session after the talk. So feel free to email me questions for general questions to Mumford just by email. Okay, thank you, and see you on Thursday. Thanks. Bye.
Thank
Sasha,
you.
thank you very much.